So they're the two problems that we've got, the horizon problem and the flatness problem. There's also a problem which I won't go into, that you can look up if you're interested, called the monopole problem, which refers to the absence of magnetic monopoles in the universe today. And if you've heard of the idea of magnetic monopoles, all magnets have a north and a south. There are no magnetic monopoles. You may just think that's natural, but there is nonetheless a problem about why we don't ever find magnetic monopoles. All of these things are going to be solved by one process. And that process is called inflation. Not to be confused with the sort of inflation that makes your money worth less year on year, but a different kind of inflation. And the idea is, at very early times in the universe, and here I'm actually talking about 10 to the minus 40 seconds or so. I'll be a little bit more precise, and I'll say 10 to the minus 36 seconds. You have a period of accelerated expansion. And so how do I do that? Well, remember, if I have the acceleration equation, this might sound like another blast from the past now. I take the acceleration equation, I have a double dot over a equals minus 4 pi g over 3c squared e plus 3p. Any equation of state, and p equals we, for w less than minus 1/3, I get acceleration. And the easiest thing we do is we do w equals minus 1, lambda, or the cosmological constant. And that gives a solution to the Friedmann equation, which is a of t is proportional to e to the hit. And I'm using this hi here. I'm going to call that the Hubble parameter at inflation. And so what I'm talking about here, just to be clear, I'm talking about something that looks like and mimics the cosmological constant. I'm not saying that what was responsible for inflation at 10 to the minus 36 seconds is what's responsible for the cosmological constant that we observe today. But let's just now look at what the history is going to be if this is our model. So we're in the radiation-dominated era. So early on, we have A of t is just equal to some scale factor at the time this inflation is going to start, times t over ti, and ti here is a time of inflation to the half. So at times less than ti, start is ti. That's just going to scale as a radiation-dominated universe. And then I have a period of inflation. And at the period of inflation, I start, of course, with the scale factor ai at time ti, which is the scale factor at the start of inflation. And then I multiply that by an exponential of hi t minus ti. And that's for some period ti less than t less than tf. So between the start and finish of inflation, I just have this exponential growth period. And then, of course, at some point that stops, and I have the scale factor after inflation, which is ai times the exponential of hi tf minus ti. And then, of course, I just have the t over tf to the half. I go back to being radiation dominated. So I have a period here where I'm radiation dominated. I'm then something that looks like lambda dominated. And then I go back to radiation dominated. But crucially, in the meantime, I've got this bit in here, which is my exponential growth of the scale factor. And what you commonly say is that you can look at the difference between the scale factor before and after. You call that A TF over A TI, and we'll say that's e to the n. And if you look at this little exponential here, this is what's called the number of e folding times. And you can think about this because you've got the change in the scale factor is the exponential of hi times, let's say, tf over ti minus 1. So if tf equals 10 to the minus 34, ti equals 10 to the minus 36, then n is about 100, and it's 99, effectively. Then n is about 100, just for simplicity. And so this is a very short time, right? 10 to the minus 34 seconds this happens in, although it's worth noting that's 100 Hubble times, right? So at the age of the universe, you know, the universe is 100 times older at the finish of this than it is at the start. But it's worth pointing out that n to the 100, or e to the 100, is about 10 to the 43. So this is very rapid changing of the scale factor. So in a factor of 100 in time, it increases in size by a factor of 10 to the 43. And sometimes people say to me, you know, how can you sort of give me a visualization that I can understand? You know, I take this and I increase it by a factor of 10 to the 43, how big does it sound? But the problem is that if you take basically the smallest thing you can think of, you know, an atom or an atomic nucleus or something, and you multiply it by that number, you end up with something that's bigger than the visible universe. And so what this does actually, and this is quite an important thing to think, it takes something even smaller, it takes something called quantum fluctuations. And this is basically the quantum messiness that you have in a vacuum. And it turns them into things of the scale of galaxy clusters. And indeed, it doesn't just turn them into them, it in fact is probably responsible for them. Because fundamentally at the very smallest of levels, you can't have a perfectly uniform region because of the quantum uncertainties that exist there. And those quantum uncertainties get multiplied by inflation into things which are the size of galaxy clusters. But very importantly, what this does is it takes material that was in causal contact, it expands it out of causal contact. So this stuff was in thermal equilibrium, it was actually all in the same place, and then it's been expanded away. So it solves the horizon problem very neatly. So that's one of them. What now about the flatness problem? Well, we've got our equation that we derived earlier, 1 minus omega t equals minus kc squared over r naught squared h squared a squared. Here, h equals hi always. Remember, h is just a dot over a. And for an exponential, e to the hit, a dot over a is just hi. So the Hubble parameter is always hi. So 1 minus omega at the time of the finish of inflation it's 1 over a squared, which is proportional to the exponential of minus 2 HIT. Because it's squared, remember here, a squared. So it essentially changes by the exponential of minus 2n times whatever it was before inflation, the modulus thereof. So for n equals 100, 1 minus omega TF is equal to 10 to the minus 87, 1 minus omega TI. So suddenly it's not so surprising that the universe looks flat, because if I'm anywhere within 87 orders of magnitude of being flat, then by the time I've gone through inflation, the universe will look flat. Therefore, it's not fine-tuned at all. If you have inflation, it's an inevitability, almost, of any universe that it will be flat. And so in principle, you could draw something. You could draw a very bad diagram, because my diagrams tend to be fairly bad. You know, showing T, and then 1 minus omega, if you like. And so in a radiation-dominated universe, right, 1 minus omega is growing with time. You then have inflation, and inflation just flattens the universe like this, very quickly. Of course, this is a sort of log of log things, and then we're now. And in principle, of course, depending on what lambda does, in the distant future, if you don't have lambda, it may increase again. Of course, lambda will act to flatten it, because lambda does exactly the same thing. So, in principle, therefore, the universe is not flat because it chose to be flat. It's flat because inflation enforced flatness upon it. And so those two problems, the horizon problem and the flatness problem, are both very neatly solved by inflation. And indeed, the monopole problem, the idea that you have lots of monopoles at some point, is also solved by this, because if you imagine, even if you had lots of monopoles in this volume to start with, right, the monopoles are going to be spread out over this increase, essentially, of 10 to the 43 cubed, because it's a volume effect. So the monopoles just get washed out. So, you know, that is also, without going into what the monopole problem is, the reason inflation solves that problem. So inflation looks very appealing as a solution to these issues with our benchmark cosmology.